In this video, we're going to extend an idea we've seen a little bit earlier, where we don't necessarily know all the numbers. In this particular example, in this particular video, though, we're actually not even going to have a formula for what we're trying to optimize, at least not all written out in terms of x's or t's. The reason for that is we're often looking for general behaviors, say in biology or economics, and we might not actually have formulas that apply in the general case. We don't necessarily know how to rank species by their evolutionary strategies, but we can say some fundamental things about the kinds of relationships we'd see. In those scenarios, we don't have an ability to take derivatives of a formula because we don't have a formula, and we're going to see some very common, in those cases, we can't simply take the derivative of the formula because there is no formula. We're going to see, working through an example, how that might appear, and then how we can get around that restriction and still identify optimum values. Here is a scenario we're going to consider. Imagine a chipmunk which is stocking its nest with acorns. And the way chipmunks do this is they run out and they grab acorns and then they bring them back to their nest. Now, one of the challenges they have to face is they can collect more acorns on a trip by just stuffing their cheeks more and more full. But what happens is there's a diminishing returns that it kicks in after a while. And we can see this in this graph here. As time goes on, and let's emphasize that this is for one trip, the chipmunk is quickly able to stock up on nuts, being able to put them in their cheeks when the cheeks are pretty much empty. But then as their cheeks get more and more full, it becomes harder and harder to put more in. They spend more and more time just adjusting. And we get this concave down relationship, increasing but concave down, between the amount gathered and the time for the trip. This is also called the load size. Now, there is one extra ingredient here, which is this tau. That's a frequently used symbol in biocalculus, which represents the travel time and includes the travel there and back. So the total travel time there and back. Then once the chipmunk has arrived and then harvests, so this is really the harvest time here, or the collecting time, we see this growth. They're able to put more food in their cheeks, and then they're still able to put more, but it becomes less and less efficient. If we imagine some fixed time t is when they stop this collection, then tau plus t is the total travel time, and that's captured down here. Thinking of this from an evolutionary perspective, what would be the most advantageous for the chipmunk is to maximize this average collection rate. In other words, how quickly or how much food is gathered per unit time. This gets away from the whole issue about travel time versus collecting time. We can call this rate R of t, and it is going to be the amount collected divided by the time. And because of the way the information was presented, this is really the amount collected per trip divided by the time per trip. So with that ratio, we can say we collected 10 nuts per trip and it took us 5 hours. Okay, so we have 10 nuts every 5 hours, or that would be 2 nuts per hour. Where do we see that in our graph? Well, if this is our f of t, and it starts here, goes like this, well, literally the amount collected per trip is this function of time. The time per trip, let's say it's here, and that's t. The time per trip isn't just t, though. It has this extra tau for the travel time, and we have that distance then on the horizontal axis. So we have t plus tau. Again, this could represent a certain travel time, say an hour, to get to the collecting site, and then whatever time we decide to harvest for, that's going to give us the total time for one trip, and f of t by itself gives us how much would be collected in that time. Now this is an interesting function It's the kind of thing we've seen before because it looks like a ratio of y values to x values, or vertical values to horizontal values. That should ring some bells from earlier in the course. Taking a look at that r of t function again, f of t over t plus tau. Here we're given the explicit hint that we could be looking at that as a slope. This is, if we like, f of t minus 0, or a delta f. Let's put this a bit further down. There we go. And the denominator is also a delta t. Let's do this. Tau plus t, or t plus tau. That is a total distance in the time frame as well. Where do we see that, or where can we visualize that as a slope? If we pick a time t, and we go up to this value here, f of t minus 0 is this distance here, delta f. There we go. And delta t is this total time down here. And if we're asked what the ratio is, that is going to be a slope connecting those 2 points. The change from 0 up to f is f of t. The change on the horizontal distance here is t plus tau, or delta t, and the rise over the run is going to be that slope. So this is a new construction using some insights from earlier in the course, but it lets us instantly construct something that shows the ratio we're interested in. What do I want to make as large as possible? I want to make the ratio of food collected per trip per travel time as large as possible. That's going to be maximizing the slope of this line. Now, students are usually more comfortable working with particular numbers, but we're going to step away from that because the general formula for this graph here isn't something we would know. It would change a lot depending on individual situations. What we do know is that it would roughly have this shape. So let's try to look at our rate function, and we know it's built of this concave down harvesting function all over t plus tau. And from that, we can actually get the derivative. Not explicitly, but we know that this is a quotient, and so we can talk about the derivative of the top, f prime of t, times the bottom, t plus tau, minus the top times the derivative of the bottom. Key thing here is the travel time is just a constant, whereas t is how long we're taking on each trip. That's the variable. So the derivative of the denominator would simply be 1 plus 0, all over the bottom squared. That looks horrible. That is not particularly helpful, but what we're going to do is set that equal to 0 for critical points. In other words, if we're looking for the optimum rate, what's going to maximize or minimize, but here it'll pop out as a maximum, the maximum rate will occur when the derivative equals 0. Well, that becomes an interesting thing to solve for. What can we say about that? Well, what we can do is multiply up this t plus tau. It multiplies by 0 and goes away. We're then left with this expression. We can bring the f of t to the other side, and we have f prime of t, t plus tau. And we can actually bring this down to the other side as well. So f of t at t plus tau equals f prime of t. Wait a minute, that looks familiar. Looking up, hey, that was our average rate. So let's pause here. This is not obvious to interpret, so I want to take their time with it. But the optimal rate of collection occurs when these two things are equal. This is the average rate, and it was the slope of that line in the previous graph connecting this point to this point. When that slope, which is r of t, is equal to f prime of t, which is the instantaneous slope, that equality is going to mark when we're at an optimal rate. And that is something that is not obvious at all. Let's see this in context of the graph and see if it makes more sense there. But keep this calculation result in mind. Take a look at this example here. There are 5 points selected. Imagine which of these points is going to give the maximum value for r of t. We'll pause. I recommend pausing the video, experimenting a bit, and then we'll take a look at how to work through this together. Okay, let's take the naive way first, which is simply to draw each of the slope lines that represent the r of t values. So we connect this point and find the slope of the line that links it to the point C or B and so on. And what we can see is each of these lines have a different slope, but the line B seems to have the highest slope. And higher slope means larger rate. So B has highest r of t value. How much can I collect per unit time given this collection rate? But could I figure that out beforehand? Absolutely. The extra condition that we found on the last page was the optimal rate, the steepest slope, is going to occur when that slope that we just drew is equal to the instantaneous slope. So imagine drawing the instantaneous slope at B versus D. You can see here that the green line, the slope of that, and the red line are very, very different. But at this one optimal point at B, the slope that we get for the rate is equal to the slope that we'd have at the instantaneous point. And so at the optimum, or at the optimal travel time, we see that condition that our, let's call it point here, little b, that slope represented by the average is going to equal f prime at that same point. Instantaneous slope, or tangent line slope, whereas this is the average slope. What we've done here is look at the slope that we defined as the thing we care about most, the average of the collection rate, and recognized that that is going to be highest or best or optimal at a very specific condition when those two slopes are actually equal, the average slope and the instantaneous slope. Now this result actually shows up in a number of different contexts. This is actually known as the marginal value theorem in economics. There are similar phrasings for it in biology, and it tells us that we get the best result when our current average rate of harvest becomes equal with the instantaneous rate of harvesting. Again, this is our f prime, and this is our r of t, which is that long ratio f of t over t plus tau. So they're both slopes. One's a derivative, one's an average rate, but they're both slopes, and we get the optimal behavior when those two things are equal. This can be applied, to, as I said, to economics as well as biology. So it's a far-ranging idea, and we did all of it not knowing explicitly what the formula for f of t was. That didn't slow us down from being able to do critical point analysis. It just meant that the result that we obtained looked much more general, and so in fact applies in more scenarios than if we had known a formula for f of t.